Yes, I can hear you.
Hi, this is Dirk.
Sounds like
I
you're
hope you can hear me.
Crosstalk.
Sorry,
Dirk,
could you
can
hear
you
me?
try
Yeah,
again? Yes,
this is
yeah, I can hear you.
okay. Thanks.
So let's get started. Okay. Hello everyone. Welcome to RTGWG interim. I'm Yingzhen and I have my co-chair Jeff with me. So today we are going to have an interim on semantic routing. For interim meetings, the IETF note well also applies. So all participants need to follow the IETF process and policies. If you have any question about Notewell, there are pointers on this slide that you can look into more details. If you have any questions, you can ask the chairs or the ADs. So we'll follow all the IETF IPR disclosure policy as well as RTGWG process. So here are some logistics about this meeting. Please be aware that this meeting is recorded and will be publicly available after the meeting. Please stay mute during the meeting, and when you are invited to talk, please make sure identify yourself and speak. Join the meet icon queue for questions. And feel free to use the chat window during the meeting, but please make your important point available at the mic so everybody can know about it. For notes taking, we have Hatchdoc, so please contribute there, especially for people who ask questions or make a comment. Please make sure it's captured there correctly. All the meeting materials are available in the link. This is the agenda for today. Please take a look, and if you have any question, speak up now.
Dear speakers, please note your times. Please try to keep yourself within your time limits. So you're going to eat someone else's time.
Yeah. Otherwise, let's get started. So we will have agent to take control of the meeting.
Thank you. I don't know whether anything in the IETF has ever been under control, but I will do my best. Just a quick note, the HedgeDoc link on the slides was wrong, but that is showing correctly in MeetEcho. So people, please jump in and make notes. Great.
Okay. Yeah.
So the purpose of this meeting, I think, is to give a little bit of an airing to what semantic routing is for and what problems it's trying to solve and how, and then discuss what a possible architecture solution might look like and float some straw men as technology approaches that might be used one day, possibly, if semantic routing needs work. It's not attempting to push solutions out there at the moment, but more discuss the approaches that could be made and see whether we can burn those straw men and move forward. So I think we should leap straight in and Daniel should go ahead. I guess, Dan, if you ask to share slides, then the chairs will say yes, and we'll get the right slide set.
Yeah, all the slides have been preloaded, so people can just use the preloaded slides. Yeah.
Cool. Okay, thanks, guys. Let me just start my timer here, make sure I stay within time slots. So what we wanted to do at the start of our session here was just provide a refresher on semantic routing and give you some background on why we've been sort of investigating the topic, some of the use cases, and a couple of links to existing documents that you may find relevant. And then we'll build on the architecture discussion, potential sort of complementary ancillary technologies, and then where to, which direction should we be heading after that. Cool. So what's actually driving some of this discussion? Well, ideally, at least in the IETF, it is problems, requirements. And although some of our early semantic routing discussion took place within the IETF, i.e. sort of the research sphere of influence, we are very much mindful that there are applicability / use cases for semantic routing already in commercial environments or near-term commercial environments. Now, I could spend a few minutes talking about the tens or hundreds of potential use cases for this type of technology, but that's really not necessary because we've all been drinking the Kool-Aid as to sort of what future internet will look like and enable us to do. But really, my main use case is on the next slide, and it's specifically around intelligent medical devices, so smart med type technology, and I'll talk about that in a moment. But I think it's worth just reminding ourselves that there are several additional use cases that may be relevant for some people either on the call or others who may start to look at this technology in the future. We know that the cloud is sort of dominant now, and essentially the internet to a certain degree is providing interconnectivity between cloud resources, whether they're sort of hyperscale cloud or highly distributed sort of fog architecture. And yes, we're going to be talking about capacity and QoS. So essentially we have fairly ubiquitous connectivity with high bandwidth available across those links. So the use case that I'm kind of interested in fact, in the spirit of full disclosure, there's two use cases, but this is the one that I'm going to talk about today, and that's sort of the health network. And certainly in Europe, we're seeing significant activity for this particular use case. There's several European Commission funded projects and EPSRC funded projects, that's the UK Research Council, that are bringing together telecommunication experts, researchers, clinical and hospital sites, as well as SME type stakeholders. And that's to provide connectivity, sort of network infrastructure that can connect several emerging devices that are going to be used for patient care. And also, well, this is not just kind of proactive patient care that's maybe monitoring your blood pressure or cholesterol or fat content or glucose, etc., but also reactive devices that in some situation you have a particular problem with your health, it would sort of trigger a critical alarm and various sort of remedial actions would be taken. And these devices have numerous requirements. There may be, in terms of networking requirements, there'll be devices that have to be always on, connected, low latency, minimal bandwidth. There will be other devices maybe connected to MRI type devices that are used sparingly, but actually very high bandwidth, super high resolution photos and graphics, spectrometers, etc., and everything in between. Some of these devices will have various stacks running directly on top of them. Others are fairly dumb. They have sort of one task in mind, and essentially will have to be interconnected through various gateways that will have an IP stack, but it has very limited capabilities. So it can't participate in various overlay technologies. And why is this an interesting use case? Well, clearly it's for our benefit. It's massive in terms of sort of growth. And I think it's just underlined by the revenue opportunity as well, which generally money sort of talks, and that funds a lot of our research and technology development. Now, we could just look at historic methods of meeting some of these requirements when we define our problem statement and define the use case. But actually, we're going to, oh, I've got a request to go into slide deck mode. Okay, I'll try that. Problem is I've got multiple monitors, so now I have to stop sharing and reshare my screen. But while I do that, I will try to multitask. Essentially, we need to sort of take a slightly different approach with solving some of these problems. I think, Adrian, you have to give me the screen share again. Thanks. Okay. There we go. Should have a happy customer now. We can't just build out new infrastructure and expect to throw unlimited bandwidth at it. And that's a discussion that we're going to have later. We could jack up our QoS capabilities, provide more memory and CPU, i.e. more state to devices, more logic, more capability. But that just increases the cost of the physical element as well, and maybe requires some essentially overhead for packet processing and forwarding. Maybe we should sort of reconfigure our topology. That makes sense, especially when we're looking at low latency applications. Maybe we should just throw away existing IP stacks or legacy stacks and invent something new. All of those are potential options, I suppose. What are we looking at here? Well, essentially, every one of you is an expert and will understand the architecture here in terms of routing. It's tried and tested for many decades already, and what we're advocating is semantic routing, which will augment existing sort of IP architecture in order to meet some of the emerging requirements and solve these future use cases. Now, maybe semantic routing is is not necessarily a clear term, considering the scope of the work that we're having to investigate here in the problem space and the potential solutions. Maybe semantic networking might have been a better starting point, and it's something we can look at in the future. It is not an overlay technology per se, and it is not a new traffic engineering technique. Essentially what we're doing is using existing information in the header and determining the path or the way that packet should be processed in order to reach its destination. So there are sort of three major elements: the routing aspect, and of course there are multiple methods to achieve that, the packet marking, and then ultimately forwarding, or indeed dropping the packet as well. Oops, sorry. So historically, yes, we've got Dijkstra and various other techniques, event-driven algorithms for forwarding traffic and deciding what to do with traffic. Yes, we've got control plane technology that can be either distributed or centralized, or some kind of hybrid. These will still be used. This is not, to overuse a ubiquitous term here, an SDN approach to networking. It's actually taking a more pragmatic approach to networking with existing technologies, augmenting them with some new innovation in order to meet expanding, maybe evolving use cases. So there are three elements, as mentioned: the routing. Maybe there's an element of path computation as well to decide, where to place your paths in the network and when to modify them. Then there's the forwarding, which as mentioned, the instruction for how to process the packet can be sort of taken locally, or it could be managed using a centralized entity, and maybe that's hierarchical as well, where you've got local decision makers for specific types of traffic that are then sort of groomed or controlled by some higher level controller, for want of a better term. And that higher level controller can also perform some re-optimization at specific points in time, or in the event of some sort of failure, catastrophic failure in some cases. One of the sort of sub-use cases that we had for the medical domain was field hospitals that might be set up in the event of some sort of natural occurring disaster, where you essentially have sites coming on and off line and joining the network, where you've got patients being treated with different injuries, and then devices that are providing patient data, having to store that information at central locations. That data needs to be clearly differentiated, and in that kind of environment where it's ad hoc, actually setting up traffic engineering rules and using some overlay technology would be extremely problematic, and it's likely the devices deployed wouldn't support that either. And then the second part of semantic routing, or semantic networking, if you like, is the marking. Now, we've got some pretty cool tools already in our toolkit. So we can use really anything in the IP header, or the length of the packet, or maybe some meta information as well. Oh, slide has not moved. It's moved on my screen. Maybe it's being updated. I'll just bounce that. Hopefully you should see packet marking, part of semantic routing. But maybe actually we will use new bits. Maybe we're going to use new fields in the header, and I suppose that's one of the discussions we can have during our session today, is that there are new methods, new encapsulation types, new extension headers, special purpose labels potentially that could be used. I suppose one of the design goals of semantic routing or semantic networking is not to constrain the solution that you might use in order to achieve the objectives. What we want to do is essentially say, well, for some situations, you might use foo technology, and for other situations, you might use an entirely different encapsulation or packet header information. Okay, if any of my previous slides haven't been contentious, maybe this is the first contentious issues. The bold statement here is semantic routing or semantic networking, architecturally speaking at least, is not a big deal. And I know that some people might disagree. This is the IETF, and that's really what makes it so cool. But what we're not doing is redesigning IP routing. We're not breaking the internet. We're not saying this specifically applies to a greenfield network and you must rip out and replace all of your existing equipment. What we're saying is this is a set of objectives with capability and architecture that augments existing technology. So in terms of traditional sort of identification and endpoint information, the IP address, great, we will continue to use the IP address. It's just that now we're going to have a semantic element that's applied to it. And if you're a device that supports semantic networking, great, you might understand it and do something with it. If not, cool, just ignore it. It won't break that particular network. But for certain situations where we need additional information to be encoded and used for semantic networking, maybe it's not just the IP address that we're going to be using, but there's other packet header information. In terms of how we discover state and disseminate it, or populate sort of forwarding tables, or modify the logic or sort of the policy that we want to apply at a forwarding point, well, those may require some modification, but we're not talking about replacement of all of the cool technology that we spent a decade or more designing. So why are we here today? Well, this is a discussion that started in the IRTF, and there are some really interesting threads that have been picked up, and we're following those. Then we kind of highlighted the work a couple of IETFs ago in the routing working group, and there was strong response to that, positive, I believe, because there are clearly a lot of routing experts who are kind of interested in this. Even if that interest is simply saying we don't need to do it, that's great. Let's hear that. There are numerous documents that we've tried to write in order to document the requirements and some of the use cases, some of the objectives. So now it's really just about continuing that discussion. Thank you. That is my presentation.
Thank you, Dan. I think that's a good quick introduction into what's going on. I don't see anyone in the queue, so maybe it's clear to people. Oh, I do see people in the queue. Sorry.
There's a number of people in the queue.
Yeah.
Linda, you were the first. Please go ahead.
Thank you very much for the nice presentation. Just have a couple of questions. So you focus on the medical device. So today, most medical devices, like I know lots of people wear those continuous monitoring, glucose monitoring. You just go to their phone, and then the phone reported directly to the server or whatever in the cloud. So I'm just curious, like in that case, the medical device environment, the semantics, what is the information carried by the semantics? Are you like forwarding based on the name of the person or the name of the disease, or what exactly? Can you elaborate a little more?
Sure. Just one observation here as well. Whenever I unmute my mic, it actually blocks the audio. So TV, radio. So why the medical devices? Well, actually, it's potentially going to be funded specifically to help us develop semantic routing as a technology. And the CGM example, the continuous glucose monitor, is nice, but that is a more traditional device. So you would have a patch that sits on your arm for 2 weeks. That's essentially providing glucose information reading. That's pretty cool. And unless it drops below a particular point and you slip into a coma, that would be bad. Or exceeds a particular threshold, and then you need to pump some insulin into you, then you would have to potentially prioritize that traffic to a particular server in order to get that notification, in order to avoid any kind of problem. Now, not everyone, of course, has one of these sensors or a sensor that's kind of Bluetooth or NFC enabled. So there are much cheaper devices that maybe have a local gateway that you want to use. Maybe you've got multiple patients at a particular site. But that particular device aside, there are other devices that might sit in your home and be used for things like sort of EKG or in a hospital. I mentioned with the MRI and things like that, in a hospital that's basically set up in the event of some disaster. There's not going to be high capacity connectivity, so something will have to manage the bandwidth in and out of that site depending on sort of real-time requirements.
Thank you.
All right, I see Hisham next in the queue.
Yeah, thanks, Dan, for your presentation. You mentioned that that can use some information in the payload for semantic routing, right? So I was thinking about the media-aware network element, which can look into RTB information about like the image or the video encoded, and find out if this payload carries important information that we need to send it to the receiver. We don't want it to be lost or discarded.
Yeah, so I think what
then we can
do here
route
is
traffic
have
into a
something
less
that can mask the
congested
packet and specifically then treat that packet in a particular
please
way.
don't talk over each
So
other.
we would ideally be able to kind of mark traffic and then set up connectivity based on where that traffic needs to go and what maybe network requirements it has in terms of latency and bandwidth and jitter, etc. The payload inspection, potentially there is sort of hardware now, low-cost white box hardware that's capable of looking at the payload. But then, there's a whole set of other issues that potentially opens up in terms of encryption and privacy as well when you start digging into the payload. But it's worth discussing, but it's not something specifically we focused any time on.
Okay, thank you.
And last before we move on is AC.
Yeah, okay. This sort of reminds me of APN because this is really just another application. And this has already been, application aware networking. Like you said, it isn't a big deal. It's already been done both for the QoS and for the routing decision. But and all, the well-known applications, they have a certain fingerprint, so they can be recognized without, within an environment under administrative control. These can all be recognized, well-known applications, be their fingerprint or 5-tuple or whatever, without any additional marking. Now, what you're saying is, so we standardize both the marking, the identification of the critical applications and the behavior, both the treatment of the packets and the routing decision, which is, like I said, this has already been done. How do you make sure that if once you standardize it, that people are being truthful? Because everybody's going to, everybody's going to want, whether it be, somebody who's gaming, they'll come up with some way to get the same priority that these life critical applications are. And unless it's under a single administrative control, once it goes over the public network, all bets are off. And also, this is going to cost more money to get this treatment. How are you going to administrate and bill for these critical applications?
Oh, great questions, AC, and I like the way you think. I will, in the interest of time, I will defer somewhat some of these responses because I think we will cover them in more detail as we go through the session. In terms of things like stopping people maliciously attacking the system or trying to game the system, then it would be a sort of, what's the expression, trust but verify, I've heard before. Regarding the APN aspect, I will defer that to Adrian because he chaired the APN session, and it is something that's been mentioned previously as well. So I will end my my response there, and hopefully, AC, we will pick the rest of the issues off during the discussion.
Thanks, Dan and AC. I think AC is asking the right questions. With regard to APN, I bounced all this off the APN people because you're right, it looks very similar. And the APN guys said that they were principally interested in per hop behaviors and not in influencing the forwarding or even the routing part that determines what the forwarding paths are. Now, I think this is all open for discussion, but that's how we got where we are. So we should move on and let Phil talk. Phil, although he's speaking in a personal capacity, works at a service provider, and I was particularly keen to get a service provider perspective of QoS and so on.
Let's look at particularly, so Thanks, Adrian. Should I share my screen or
You can
will the
ask
chairs share?
to. You can ask to,
Okay, I'll ask to share.
share slides. Yeah.
Yes. And then I go on. Has that come through?
We see that, and if you could go full screen.
Let's see.
Go full screen.
It's not like it's the same, definitely it's not the same device, as you can see.
Someone
Okay.
is talking over and it's unclear who. Mitaka doesn't show the name. Guys, please go on mute if you aren't speaking.
Yeah, thanks very much. So I'm Phil Eardley, as Amy says, talking in a personal capacity. Thank you very much for the invite to do this kind of brain dump about quality of service and maybe a bit of a perspective on semantic routing. So I thought I'd just start with my understanding of semantic routing, that it's about differentiated forwarding behavior and differentiated paths of routing. So it feels very much in the sort of quality of service area that it's about. I think if I've got it right, it's trying to do inter-domain as well as intra-domain. And you know, the phrase from Dan's slides that it's about hop by hop and packet by packet semantic routing stuff.
Phil, your slides. Your slides are not advancing as you're progressing.
The slide didn't advance. Oh dear.
No.
Right. I have no idea how to do that then. I've just advanced them on my view of PowerPoint.
Try to go into presentation mode.
I had done that, and actually
I think it is in presentation mode. So I should end slideshow.
Perhaps I might want to refresh my memory. So I don't know where.
So we can see your slide changing in size.
Can you try
So
to
that-
share
that-
the preloaded
Yeah, now it's
slides?
moving.
Okay.
That works, does it?
Yeah.
Yeah.
So something to do with going in full screen. Do you mind if I share it like this then? Because I don't need to get rid of that. Let's get rid of that. Right, I think we just have to live with it. Sorry. So yes, semantic routing is, you know, is hop by hop and packet by packet. And Dan's phrase, I'm not sure if I've taken this out of context, is that it's quas on steroids. Apologies if I have, but I thought it was a nice phrase. So to give you some of my views on quality of service, so I think the first thing to say about quas is it's really trying to buy you a time advantage. So the schematic at the bottom is supposed to indicate that, you know, we've got a whole range of applications that we can do now and we might want to do in the future. We have some, you know, like VoIP now very easy to do. We have got some like I don't know, remote surgery, which are not yet possible. And then we've got some which are kind of on the edge of being possible. So it's really those kind of ones in that amber zone. So the ones which are sort of almost possible, but not quite. Those are really the ones where quas mechanisms are buying you an advantage because you can, you know, they become feasible. But of course, this is all in time. This is all shifting to the right. So as you get more bandwidth, you know, you can do those applications like say immersive virtual reality, which might be sort of barely feasible now, become easy. You know, so in a world of growing bandwidth, especially where bandwidth is growing quite fast and this edge or critical edge is moving to the right, quality of service is really giving you a time advantage. It's not doing anything beyond that, things will become feasible. So to point out something obvious, that means that the quality of service mechanism you introduce, you've got to introduce it quickly enough that you're not losing that time advantage that you just think you're gaining. And also in this perspective, QoS matters more where bandwidth is constrained. So that would have been true in in edge networks in the past, is probably much less true today with sort of fiber and 5G. And in situations where capacity is hard to deploy, there'll be some environments where it's actually difficult to go and put in new capacity. So they would also be things where you get. Is somebody trying to say something? Okay, I'll keep going.
Full screen mode. There's lots of comments in the chat about that.
Sorry, I didn't catch that at all.
Please use full screen mode.
I will try.
Also, it seems like you might have CNN or something on in the background.
Not me, I'm afraid. Well, it's. Don't know if that's somebody else on the call, but yes, I haven't got CNN on. So the second caution I wanted to make about quality of service is, QoS is not something that's creating capacity. It's resharing capacity. So sort of an analogy I'm drawn here is with the first and second laws of thermodynamics. So thermodynamics says, sort of first law says that you can change energy from one form to another, but you're not creating it or destroying it. And then entropy in the system will either stay the same or increase. So similarly, you're not creating capacity with QoS. You're resharing it differently between users, and you may be losing some of your capacity through the QoS mechanism that you've added in. So you should have those as sort of cautions to remember. But on the positive side, there are lots of things that you can improve, which are kind of in the sort of the quality field. So things like latency with AQM measures and buffer management, and ECN and L4S kind of things. There's lots of things you can do there that are really good. On reliability, so kind of failures are a form of QoS degradation. So mechanisms that improve reliability are really important. Energy is becoming more and more critical, partly because of energy costs going up and us wanting to be greener, partly because power efficiency is not increasing at the same rate as bandwidth and network growth is. So the fraction of cost for energy is going up in your network. Lifetime energy costs are now expected to be kind of comparable to CapEx. So it's really important that you work on it. And forwarding takes energy. So you've got to make sure that you try and think about how often you hit forwarding hardware and those sorts of things. On the security front, I think security is very closely tied into quality of service. So like MPLS and VPNs, the two things are very much tied closely together. Multipath stuff is all cool to either packet by packet for efficiency or kind of path alternatives for resilience. And automation is a sort of key strategic goal for all operators. So those kind of things are really important things to keep in mind. And the third thing I wanted to say is that when you do QoS, you've got to be, I think you've got to be aligned to a commercial model. For me, that's the lesson that came out of the QoS 3869 RFC and the sort of difficulties of deploying QoS at the beam. that you've got to try and align to a commercial model if you want to be successful in this. And there are examples where it does align with the commercial. So like wholesale costs, for instance, where a global operator or an over-the-top buys capacity or quality service from a local operator. So those things are well aligned with the commercial model, where you're managing stuff at the ingress, and then within what you've paid for, then you do cross to kind of share within that, how you divide it between your different users internally. Those are ways where it's well aligned to the commercial model. So kind of things that have been successful. And just in some sort of related considerations to think about in this commercial model or related to it, be careful that you don't add additional security or denial of service risk, and that's kind of the point that AC was making. How come you've got to make sure that you don't just have everybody using the top priority. We've got to think about complexity that it adds to the system. As complexity makes it more expensive to operate and manage, and more expensive probably to forward packets and to do the routing. And we've got to think about incremental deployability, and FRC 5218 talks about aligning incentives and aligning the pain and gain if you want a protocol to be successful or an approach to be successful. And just finally, sort of some conclusions relating that quality service stuff back to semantic routing, which I'll pose as some questions that I think need to be thought about for semantic routing. So the first one off that first slide, why is it better than buying bandwidth? Got to have a clear answer to that question. And from the second slide, well, with semantic routing, who's losing? So which individuals or which customers are losing, and what becomes harder through doing it? And
are you trying to advance your slides because they aren't?
And
Philip?
Sorry, yeah. Let me just.
We are still at QS doesn't create capacity slide. Yeah, it's moving now.
So, yeah, and the third kind of question I pose that semantic routing to have to think about is who pays for it and how. So how does it align to a commercial model for this stuff? I apologise that the slides weren't advancing. It seemed to be couldn't do it in both full mode and slide advance, which is a bit tricky. I'm not sure why that was.
Thanks, Phil. Someday someone will invent a slide sharing application that you can use. I got myself in the queue first because I'm conscious that you have to run away from this meeting soon and might miss the discussion at the end. I wanted to ask you, well, firstly, pulling in, there was a comment in the chat quoting Peter Lothberg, basically saying that QoS is about deciding whose packets you're going to drop. And I think that's certainly part of what you were saying there about people lose. But that seems to be a bit of a PHB, per help behavior kind of view of QoS, rather than a routing view where you might be putting packets onto paths that are more appropriate for the service that they want. And that sort of leads me to your commercial point, which AC made as well, which is how do you stop everybody asking for the best quality of service? do you believe that there are pricing models that could be applied to customers, even possibly end users, where they subscribe to like a gaming connection service compared to a file streaming connection service?
Well, people have talked about, on that second point, people have talked about it, and it's been very hard to have any success in that, at least at the individual consumers. People just buy bandwidth, or they just buy a connection that's good enough. I think for businesses, you've got, there's more of a chance, and people, I mean, there are successes in that, aren't there? Because MPLS is arguably doing that. That the businesses are prepared to buy different services, and you manage into them. On the routing paths, I guess I'm not sure I see what the real difference will be between the routing paths, except possibly if you're doing some additional processing en route, sort of computing stuff en route, and then maybe there's only some routers will have some types of processing there which others don't, or a particular server that you need to get to because that's got the data needed or something.
Okay, thanks.
But I think
Linda.
trying to link that routing into more of a sort of real-time thing is really difficult.
All right, Linda, you're up.
Philip, thanks for the presentation. So I'm just curious, like in terms of quality of service, are there any major differences between, like for the semantic routing QoS versus just the packet forwarding QoS?
The differences between semantic routing and QoS mechanisms.
No, I'm saying like semantic routing, right? What's the difference between just the simple QoS we do on MPLS network versus the QoS on the semantic routing?
I don't think I'm the best person to answer that because I can't say I've got a detailed understanding of semantic routing. But yeah, it's definitely something, and I think it's partly because my impression is there's still, lots of different options for how people think it might be done. But it was definitely, I mean, that was certainly a question I had when I heard about semantic routing on an earlier IETF meeting, was what is the difference from, technology X like MPLS. So I think it's definitely, and it's an important one for the semantic routing proponents to get a good answer to. I'd agree with you on that.
So Adrian, are you going to answer that?
No, because I'm not proposing semantic routing. I think what we're doing is kicking the ideas around and trying to find out what the questions are.
Oh,
So
okay. Thank you.
You have asked a good question.
Thank you.
Greg?
Yeah.
So as time critical or time constrained applications, if I understand correctly, be one of the applications for semantic routing. So I wonder how then semantic routing is related to deterministic networking. Is it alternative technology? Is deterministic networking is one of their methods to realize semantic routing?
I think that's another good question that people should have a nice answer to. Mm-hmm. Yeah, because some of the applications people talk about are very much in that highly demanding, time-sensitive networking kind of area, aren't they?
Yeah, I think Greg has. You've raised another point that needs consideration, and whether deterministic networking covers all of the bases for semantic routing, or some of them, and therefore falls into one of the bullets in my presentation that I'm going to have to rush through, which says that we're seeing a lot of stovepipe solutions, and maybe deterministic networking is exactly that. It's a slice of the problem space.
Yeah. Okay. Thank you.
All right. So I'm up next. I'm going to try and buy us back some time, especially since advancing the slides is a problem. Here we go. This is building a little bit on a presentation at IETF 113, where I was also squeezed for time. But I wanted to look at some of the things we should worry about when people talk about semantic routing. And none of this should come as a big surprise. It should just be good engineering practices of scoping requirements, designing well, and then testing, which is something that maybe doesn't happen too well as we float new ideas. We don't push them out into realistic networks to see what effect they have. What underlies this is the concern that the internet routing system is fragile, that routing is more complicated than people believe, and that historically we've done a pretty poor job of thinking through the designs and consequences and the testing. So semantic routing introduces a number of specific concerns about how it can be backward compatible with what we've already got, how we would set about deploying it, what the utility is, whether we're targeting a specific set of requirements or technology, or whether we're trying to come up with a solution that works across IP packet networks, how we future-proof. Scalability and stability are, I think, missed as manageability, privacy, and security tend to get left until the last. So let's quick deep dive on those. In terms of backward compatibility, we really don't want to break the internet. So we have to introduce ideas that coexist with existing techniques and don't break anything. And a lot of that plays into the deployability. So anything new is likely to need some form of update. And if we're playing with how forwarding works, that may well be firmware updates. And that can mean that it's hard deploying this into existing networks. There's been a lot of talk over the last few years about possibly replacing IPv6 with something new to address some of these requirements. And to me, this seems like a poor choice. I think we need something that is more evolutionary. But there are still lots of options in terms of overlays and underlays, which may be easier to achieve in a seamless way. And then coexistence or walled gardens is a way to do this in a sort of safe way. And I think Dirk is going to talk about this a bit coming up when he goes into architecture. So in terms of general utility, the walled garden approach has been very, very effective solving niche problems in private networks, and you don't have to worry about interworking. But as the number of niches multiplies up, the vendors have to implement lots of different specific solutions, and that pushes development costs and associated test and maintenance. Wheels get reinvented, mistakes get repeated, and as those niche domains start to overlap or run into each other, deployment gets complicated. So that brings us to questions about interconnectivity and interoperability, and indeed what happens when a packet escapes from a walled garden, and will it get misinterpreted or cause somebody to crash? Given that the whole point of the internet is end-to-end connectivity, shouldn't we be aiming for solutions that are more widely deployable? So wouldn't it be nice if we could invent one solution that addressed all of the current and future requirements? Which of course takes us to future-proofing. It seems unlikely that we can capture every feature and requirement now, but as Phil showed on his slide, that fairly thin wedge of things we could probably make now but are struggling to deploy is always moving towards the right, and we're getting more applications coming along and wanting services from the network. So we should aim for solutions that are extensible by design, so we can add new features with forward and backward compatibility built in. I think that means that we have to leave space in our encodings for additional data or use extensible encoding techniques. But that impacts on scalability. So that really applies to both the routing and the forwarding. Some encapsulation techniques for extensibility can actually grow quite large, and if you have too much data in the packet header, you're effectively paying a cell tax. And for some applications, maybe that's not a big deal, but it looks like the applications that we're talking about are probably sending smaller packets, and then this does become an issue. It also is potentially hard to parse at line rate if you've got a large chunk of TLVs in the front of your packet. At the same time, if you're using distributed routing protocols, you may be needing to collect more information about the status of the links and the nodes, and what the what for example the latency is at the moment. So how much information you're flooding and how often you're flooding it makes a really big difference to the scalability and to some extent to the stability. And as there are changes in the network, you may discover that you're just pushing so much data around, it's not stable. And my last point here is to consider, as we have always done, that nodes in the network need the same algorithms and and should be converging on the same information. And we need to ask ourselves whether that's something that we need to continue with, or whether there are ways to avoid looping and thrashing, but be more flexible. Manageability has for so long been the poor child of protocol development, and I think we need to look, especially with semantic routing, on the impacts that might be made on OAM. I think semantic routing makes the whole behavior of the network much more complicated and harder to predict. So we might need more and better OAM. But if semantic routing is dynamic and adapting to changes in the network, the packet tracing may not be particularly good at telling us where our next packet is going to go, given how the last packet went. Lastly, I want to pull up privacy and security. Security, I think, is maybe a little bit more simple to handle. It's about how you might cause the network to send the traffic to the wrong place or simply to drop packets, semantic routing may well be increasing the attack surface. So that needs to be looked at. And obviously a fragile network is a more easily attacked network. But privacy has had a lot of attention, and Linda asked in one of her questions about what information goes in the packet. Does it identify the user and the application they're running and so on? And I think this is essential. It must not be possible to determine a user's identity through semantic routing. That is no further than can already be done. And it must not be possible to determine what application is being run from the information. And then lastly, we have to consider the regulatory implications and net neutrality and how marking a packet might get it treated differently. So to do this, there must be no trade-off between the information needed to route and forward and the achieving of privacy. So we have to do both. And finally, my question is what to do with this. I'd like to take these questions forward into the discussion of what semantic routing is and what it might achieve. And then we can look at the architecture and the protocol possibilities. And then finally, whether to bother with any of this at all. So that's me finished. And I'm looking at, and Greg is in the queue. Hi, Greg.
Okay, greatly appreciate your pointing to the OAM. And yes, it's very interesting challenge to properly reflect their paths that being used, and especially if it's for resource and time critical applications. So I will imagine it's not only time critical, it's very similar again with the DetNet requirement of time constraint and almost zero loss.
Right, thank you. Yeah, and that's really worth exposing.
Thank you.
All right, Linda, quick one, please.
Okay, quick one. So in terms of what is semantic routing, I have that question. Is this routing forwarding based on additional field in the packet, or is the forwarding still based on the destination, but with consideration of additional information carried by the packet?
So it's forwarding based on information that's in the packet. As Dan had on his slides, all forwarding is semantic forwarding, but the proposal is that additional information can be put in there as well to accompany the fields that are there at the moment, which includes the destination. And routing can program the forwarding plane to achieve forwarding based on lookups on that information.
Thank you.
All right, let us go on then quickly. Move on to Dirk, who's got some thoughts about architecture.
Yes, thanks, Adrian. Good, yeah, using the slide sharing as well. Like the animations, but that's fine. I'm speaking to an unanimated slide, which is just fine. I'm trying to bring together the discussion we've had not only today, but also in the recent months of that work, and trying to look at possible approaches and considerations of this. Sorry, now I see the controls down there. Of the for semantic routing, and as Daniel pointed out, maybe calling the semantic networking would have been a better thing to start with. What are the questions from a architecture perspective that I think we should be asking? Well, one is, what are the communication semantics that we're aiming at? What's the type of communication we want to see the network to be doing that semantic routing or semantic networking could really realize? What are the, from an architecture perspective, what are the abstractions that we're looking at this body of work should have, and how could an architecture look like? What are components involved? What are the main interactions? But also, how does it connect to other aspects that we already know how are ongoing? And I would show this in a slide later, which is the now unanimated slide that I was talking about. A couple of words on deployment, what to consider when we want to deploy ideas, like that. Since this is a discussion in the IETF, I also have a question on what's the possible role for SDOs, right? In particular for the IETF in this space. What is it we could be talking about here? Okay, so if you look at the original purpose of the routing system, it was originally designed to forward IP packets towards destination addresses in the best effort manner. Worked really well. We used locator semantic of IP addresses as a fundamental piece to achieve that. IP addresses are assigned in the context of network topologies that allows you to build a, from a particular scalability perspective, tractable system to achieve that functionality. It's a distributed decision making in intermediary routers. And key here are the methods to select the path and the criteria for doing so. Traffic engineering may improve on just best effort, and you may introduce policy-based path steering, resource reservation, and other things, that we've discussed already in the previous slides. That has evolved. That system has evolved to a system that actually supports a very rich set of communication semantics, not just one, beyond the best effort reachability that I outlined before. And I'll try to categorize them. This is first attempt that we've done in some joint work. Unicast communication, various semantics for multicast, group-based, diffusion-based multicast, which you find very often in, for instance, distributed consensus systems, where not the entire group, but a subset in a diffusion manner being addressed. Something we introduced recently in a discussion in beer was what's called a forward request return multicast semantic, where you build ephemeral relationships very, very dynamically, for which group-based approaches are not very, very well suited. Various anycast semantics, which allows you to select either randomly or through multi-optimality or in a scheduled manner the actual endpoint out of your anycast group. And on the left side, you see who's making the selection, either the source or the network. And we also included chaincast here as a programmed forwarding of packets to the network, either per hop or in a programmed manner. Again, either the selection being done at the source of the network. So you can see the communication semantics, and you can find examples of those. I presented a draft in the routing working group in the last IETF on routing beyond reachability, which lists RFC's ongoing drafts, a bit of research work, but mainly engineering work that supports these various semantics in a very wide set of solutions. So this is not something that's being entirely drawn up new. So if you go, well, what are the abstractions that we then maybe want from an architecture? Well, we started off with an IP-based reachability where you have an IP header on which the both the routing and the forwarding decisions are being done. Packet header information, payload, and we achieved our regional locator-based addressing semantics. What I call in this slide the evolved IP routing is what we effectively see as it's described in the semantic routing draft, but also in the routing beyond reachability draft. The various methods that have evolved over time to look at various additional information in the packet header, and I sometimes call this the packet header as your oyster. Whatever you want to do, pick the field in the packet header and make an additional decision. That's the way IP has evolved in the meantime. We had an interjection back in 1996. We listed this in a recent exercise as a historical harking back into active networking, where the attempt was to change the abstraction from, in addition to the IP address, to provide a programmable unit, the so-called capsule. And those of you who may remember the original paper of 1996 will kind of like know where also the initiative in the end went to. The capsule unfortunately never took off as an abstraction module. What we look at here is a semantic header in addition to the packet header that explicitly describes and evolves from the current evolved IP routing by grouping the suitable input into the programmatic forwarding actions in a dedicated semantic header. The forwarding actions are deployed at the traversing nodes, and it's a defined place for the forwarding information to be placed. So instead of opening the entire packet header blindly, it is explicitly captured in a semantic header. So how could an architecture look like? And again, this is the non-animated slide, which is why it looks a little bit lot to take in when you stare at it at once. In the animated mode, it would have built up really nicely, but for that I needed a screen share, which I didn't dare after the previous attempts. So let me walk this maybe through from the top left. So this connects, we connect this specifically to intent-based networking. This isn't required, but it's something that we find particularly fitting, where a business logic provides an intent to an intent service manager, retrieves the mapping through an ontology in order to map the intent on some agreed concepts, and then provides the communication semantic together with the user application to an orchestration engine that retrieves the mapping of the intent onto dedicated actions, which is further constraints to the policy engine to its left side, and with the help of monitoring and prediction events to provide both constraints and metrics to the routing, to the semantic routing part, and forwarding actions, suitable forwarding actions to the semantic forwarding part. As Daniel mentioned before, these two things have to be seen in conjunction. The semantic routing provides potential additional path information to the semantic forwarding, which can then use the instructions to install and configure forwarding actions in the underlying switches and routers of the network nodes. Network topology capability states they are being obtained in the process for the routing as well and for the orchestration. And the information is being disseminated to, but also being accessed through the infrastructure links from the network topology capabilities and state component down to the network parts. This is a very high-level way of how you could look at the interaction of the various components, and a lot of more is required to dive down into what the individual bits and pieces are doing. But at a very high level, that gives you a very rough idea of how an architecture could look like. What are deployment considerations when you want to implement any of this? Adrian alluded to some of those already before. What kind of lay do we have? An overlay, an underlay, an inlay? It's important because it impacts the technical choice of realization. Right? You may use extension headers instead of messing with IP addresses, so that kicks you towards a shim overlay, a layer 3.5 as it's very often called. You may work with an underlay, which then pushes you towards segregating the existing address space within new semantics. There are examples that have done that in the past. It may have a routing protocol impact, and I know there are a lot of people that are very conscious about impacts on the routing protocol. I'm one of them, and integration with existing routing protocols or designing an overlay routing protocol are the potential choices you may have. But again, it depends on how you answer the first key question on which lay you actually do. Shipping in the night, Adrian mentioned this to reconcile the speed of rollout with the stability of the existing system. Kind of like want to have both, but you don't want to compromise in particular on the stability. And again, that may be an impact on the technical choice, particularly how, linking back to the previous question, how you answer the overlay, underlay, inlay question. Right? Is it a limited domain technology or is it multi-domain? Dan also in his example talked a lot about solutions that have been for a very long time being entirely isolated. That's okay, but how do you ensure if you come to the point not only to wanting to use the multiplexing of the technology choices, namely introducing, for instance, IP technologies in your limited domain because it's a well-established technology, but you want to interconnect, how do you ensure the interconnection now that the interconnection has been brought on the table? And there are a number of industries that are currently struggling with that, whether it's industrial networking or vehicular communication, where interconnection has come increasingly into focus from the previously very, very isolated, limited domains. How do you avoid spilling your potential domain-limited semantics into other domains? I can tell you an anecdote in the chat maybe later on how somebody at Siemens tried to solve service multiplexing and has apparently never heard of IP addresses and ports. That's one way of how you should not do that, because it will not look very nice if that packet comes out on the other side of the network. But that's an actual proposed solution in vehicular communication, unfortunately. How do you deliver new services? Is there any programmatic way of doing this? The idea of the architecture than before is that programmability is a very, very key part of making semantic networking really work in the future. That allows to roll out a lot of these semantic enhancements programmatically through the interaction with a higher level intent-based systems. How to manage networks and the increasing complexity, is it possible to move towards this programmatic execution? And the answer to those questions may also be driven by economic incentives. Again, rollout speed and scope could be one aspect that, again, may kick you to an offering on top of IPv6 because it is faster to roll out. Removing a burden to change the underlay, that's a very strong economic incentive for many service providers. And the stability, of course, of not only services, but therefore ultimately businesses is a key question. So economics play, or not just the economic model to exploit the service, but also to roll out the changes really. What are possible aspects of standardization? Why should we care about this? An architectural framework, I believe, in particular an extensible architectural framework on components, what are the interfaces and interaction, diving deeper than the previous slide that I showed. These interactions need to be interoperable. I need to know how the communication, how the protocols, how they look. What are the semantics? Not use cases, but the purpose of communication. Right, and we can map them quite easily on a variety of use cases later on. Possibly captured as a service description to enable programmatic realization. There's a lot we could potentially learn from fields like the semantic web that has done a lot of these type of service description onto service mapping type of approaches. What are the abstractions? So evolving addressing as the main input into actions and define the encodings and encapsulations that need to be done. And the actions, the state distributions, that's also known as routing protocols and the primitives that we need. Thank you very much. That was it from my side.
Thank you, Dirk. Do we have anyone with a question? Not. Okay, great. Thanks, Dirk. So we'll move on. As Dan mentioned, there are lots of proposed approaches around doing things that are routing and forwarding based on additional information. And Greg also mentioned DetNet and the work that's going there. I picked two, not because they are solutions that I or anyone is proposing as this is the way to address everything in semantic routing, but because they demonstrate some of the thinking, some of the possible approaches, and they provide us with straw men that we can either set fire to or promote into good ideas or develop and should seed our discussion. So first up is Suresh. I want to thank Suresh. He got landed with this in a bit less than 24 hours notice, and owing to some confusion, he didn't realize that he was actually expected to present anything until about 2 hours ago. But he has come up trumps and got a set of slides here and will, I'm sure, talk brilliantly. Thanks, Suresh.
Thank you, Adrian. Can you hear me clearly?
Yeah, it's good.
Yes. Yep.
So, thank you. So I just will go through pretty quickly with the SRv6 intro. I know we are running over time, so I'll try to make this extremely quick. just to go back to what Daniel said and Adrian said in their presentations, right? So like what we're trying to do with SRv6 is to augment the packet with additional information on how the packet is going to get processed in the network, right? So that's pretty much like how Daniel explained semantic routing. So like this is our semantic routing, as like Adrian would say. The idea is to add something into the packets, which is in this case is something that we call SRv6 network programming, to kind of describe a set of instructions on how to process the packet through the network. So I'm just going to skip through quite a bit of the background slides on what SR is, right? But to just talk about two data plane instantiations. Like one of them is like SR-MPLS, right, which is like a regular encapsulation of the segment routing concept over the MPLS networks. And the other one is the what we call SRv6, which is the instantiation of SR over IPv6. And the specific thing I wanted to talk about today is SRv6 network programming, which uses like IPv6 what something that looks like IPv6 addresses, or what we call like SRv6 SIDs, to establish some of the same things that the other semantic routing concepts try to implement. Just gonna skip, I don't need to preach to the IETF that IPv6 is better, but so how a network instruction looks like is pretty much, it consists of two parts. Like one of them is a locator, another one is a function. And the locator looks like pretty much like a CIDR prefix, right? You just take the locator and route a packet to that, whatever the locator is, with a given number of bits. And we have a flexible bit length selection. So like the SR node itself looks like it owns a complete prefix that's like showing up in the locator. And the function tells the node what to do. So there's like a set of predefined functions that are in the set SRv6 network programming RFC, which says like what the packet needs to, how it needs to be dealt with. And I have an example at the end if we get to it, but it tells the node like, how the packet is going to process once it gets to the node specified by the locator. So, so the network program is pretty much like a set of SRv6 SIDs, and it's got like, list of like locators and functions, right? The packet needs to pass through. So what you do is you augment the IPv6 packet with this information when the packet enters like an SR domain, and that provides what we would call like a network program for the network to treat that packet. So you put in like a whole bunch of things in a list that needs to get done when the packet goes through the network. And as the packet processes through the network, you have a pointer into the packet, which shows like what has been processed already and what still remains to be processed. So how the packet looks like, right? Like, so we have a network program in the packet header. So we have a regular IPv6 header, and what we have is another routing header that is like newly defined in the 6-man working group, which is called the segment routing header. And it's got a list of what we call the SIDs. And if you look at it, like each of them has like a locator and function, and we have a segments left, which describes like, how many of those instructions still need to get done. And using the how much segments left, you can figure out like, what is the active segment, right? Like, so, and we also do this by swapping out the destination address. So one of the behaviors would be just like take the next address sitting in here, or the next SID sitting in here, and put it in the destination address field of the packet, right? And so pretty much you just run through the program, like every node that gets the packet runs through the program. And at the end of it, the packet can leave the SR domain, and the nodes outside the domain are none the wiser. And we also have a tag field in the SR, which allows you to kind of group packets, right? So if you have a set of packets which have to receive similar kind of, I would say like quas, for lack of a better term, right? Like, like Phil was talking about before. So what you do is you tag them in a similar way. So if you have the same tag, the packets can get treated like similarly going forward. So think of it as some kind of metadata field. So we also have like a metadata TLB that can like kind of be augmented. And this is really intended for kind of a software-based solution, right? Like that we have like NFV and all those things use stuff like in a pretty extensible way. So we have some kind of separation between things that can be done on hardware, on a fast path, and stuff that are like more oriented towards like network functions, like that are implemented in software. Even though it's like a pretty, I would say, thin line between these two. So if you look at the SR itself, right, like so I would say the earlier bits, right, like the higher order bits in the SR header are optimized for hardware processing. So we here there's like a Cisco Silicon One chip that's shown here, but like we have implementations on like for example the Intel Barefoot Tofino chips and so on, and other FPGAs as well. So you can, these are like really optimized for high performance rather than I would say really being like very extremely feature rich or like very extensible, right? So that kind of like stuff that's really overflowing goes into the metadata TLB, where like software-based implementations, probably sitting in, think of it as a Kubernetes container or something, can do like highly extensible things without impacting stuff at like high volume somewhere else. So what really happens is when a packet enters like a SRv6 domain, right? Like, so the packet can be any kind of packet. It can be a v6 packet, a v4 packet, or like some other like L2 frame that enters it. What we do is we encapsulate this packet, what we call the payload packet, inside an IPv6 header, right? Like with the SRH inside. And the SRH itself contains the list of segments that we talked about earlier, which is like a set of instructions on how the packet proceeds through the network and what kind of operations need to get done on it. And I'm just going to skip through like a bunch of these things and just show you like a quick example of like what happens. But there's one thing I want to emphasize, like the packet entering the domain, right, which is like outside the SR domain, is like a plain packet. Like let's say it's a v6 packet, it stays unmodified when it leaves the domain. So this is really something that the behaviors are specified inside an SR domain. And that's why we add an additional header, put in the additional stuff. Like it's really about handling information in a domain that understands these behaviors. And like, so there's like a set of behaviors that defined by the SRv6 network programming. There's like an INI registry that talks about like, what like, numerical value is like assigned to each of these behaviors. But some of the behaviors are like, the default endpoint behavior, which is like, assigned the value 0. It just like takes the shortest path to the SIDS endpoint, right? It just like updates, it just like processes the packet and puts the next SID into the destination address and just forwards the packet, right? Like using regular forwarding mechanisms. And the cross connect is pretty much using like an IGP adjacency to send a packet to like a different node that's connected to the node that is sitting in the SID itself. So if you have, I just have a picture here. So if you look at it, right, like, so if you look at the green path, right, it takes the shortest path. So if you have an IGP adjacency, like, the packet can either flow to 124 or 134 to get to the node 4. So that's how the address looks like in the destination address field. And if you have a cross connect, what the packet happens, the packet goes from 4 to 5, and then it's getting forwarded with a cross connect to node number 6. And then it after that, it just gets forwarded to a regular IPv6 host, which is not SR aware. So that's like the the A8:::, which is like a pretty much a regular host that gets an IPv6 packet. So that's kind of how the SRv6 network programming works, and it kind of ticks off the boxes that Daniel like talked about in the beginning, to like the set of things that we need to do, right? So I'll like quote from memory, right? It's really about determining the next hop for each packet given the network sharding capability that's coming from the IGP, and we do the packet marking. Like we can talk about like how the packet is going to get treated, and like also the forwarding information is there. And we do this by placing additional information that's placed in the packet. So that's kind of how it fits into the semantic routing umbrella. So any questions?
Thank you, Suresh. And while people come to the queue, I wanted just to clarify with you the difference between marking the thing that needs to get done, so function, versus the thing that describes the packet and and, if you like, how the packet would like the network to process. Is that the difference between the function and the tag?
So the tag is really about like group policy, right? Like, so what you're trying to say is like, hey, this packet like kind of wants to get treated like other packets, right? That's kind of what the tag is really specifying, right? The function is separate, like exactly like you said, but the tag is really about like specifying similar groups of packets to get treated. So think of it as a shotgun.
Okay, good. And we have Kozik in the queue.
Thanks, Suresh, for presenting this. Like, I have a kind of a quick understanding questions. Like, what you just presented, it felt like pretty much towards the SRv6, which you know about that SRv6 segment routing. I'm just curious, like, where the key difference maker or how the semantic routing is coming. Like, is there any slide you have, additional slide kind of describes on the extension means we are doing on top of SRv6 segment routing? It's not clearly kind of indicating like the difference maker on top of what we are doing on SRv6.
You're right, Kaushika. So this is really like a toolkit, right? Like, so the semantic routing is something we can build using this. So I think like Adrian talked about, like, not like, doing like something revolutionary and do work on evolutionary things, right? So we're talking about like some kind of tools that we can use to leverage to build semantic routing. So this is like one such tool, right? Like, and I think like Stefano is going to present another one. So what you're talking about is like, taking existing networks and how can we build things on top to enable semantic routing. So like there's like a bunch of, as I said, there's a bunch of behaviors that defined in SRv6 and in NP. So if there's like stuff that's missing, we can certainly go ahead and define them. But I think it's like a fairly feature-rich solution today. So if there's like, we realize there's something that's missing, we can certainly go and add like additional behaviors on there, if that makes sense to you.
Maybe that's need to be discussed and kind of what is missing and what's the kind of additional feature sets kind of we are trying to add part of the semantic kind of identifying those would be key things, I believe, and we can go from there. Thank you.
Okay, thank you, Kosh. Thank you. Genji?
Genji, yes.
Can you hear me? Just check.
Yes.
Yes. Okay, yeah. Like, I look at the SRv6 you're using example here. Was the first presentation by Daniel about some requirement for segment routing. One thing is like not for overlay. It's called not hop by hop. So there's one thing in that slide. Here I look at your thing. Since you use some domain and then use ingress egress with something in between. To me, like you are using some counter example. Say, oh yeah, something like this. This is like overlay. Example was some requirement for segment routing for not overlay in the first presentation.
Yeah, I would say like it's think of it as more as an underlay here, right? Like like we are kind of like stuffing in stuff underneath. So I would think like this fits more on the underlay pattern, right? Because the nodes themselves are kind of unaware of this is happening. So the original like node, the two endpoints, right? Like the packet which is sending a packet, the node that's sending a packet to 1 and the ones that are receiving the packets from 5, right? Which is the original packets. They don't see this. Like, so think of it as like very similar to like how MPLS transfer underlay works, right? That's kind of how I see it. Not really as an overlay that we put on top.
Okay, well, different opinion, but anyway, thank you.
Yeah, thank you. Thank you.
All right, we better move on. Thank you, Suresh, and thank you for filling in at short notice. Next up is Stefano, who's going to talk about some work he has been doing in a similar problem space. And hopefully the slides are loading, yes. Stefano, you probably need to.
Can you hear me?
Yes, good.
Okay. Okay, so how do I move the slides?
Down the bottom of the screen, you should, when you hover over it, you should see.
Yeah, now I found it. Yeah, thank you. Okay, so hi everybody. So I'm going to present here extensible in-band processing proposal. So it is a generic and extendable mechanism to carry information in IPv6 packet headers. So referring to previous presentation where I think Adrian mentioned that we should try to find some solution which is general and extensible. So we are trying to do something in this line. So the idea is that IPv6 end system and network nodes can read and write this extensible information in packet headers. And of course, nodes can take packet processing decision depending on this EIP information. So this is not a solution which is specifically proposed for semantic routing, but semantic routing is surely one of the possible use cases that can benefit from this. And we have very recently submitted the first IETF draft with the initial ideas on this EIP. So as shown here, that there are different use cases that can be supported. So semantic routing is one of these. Another one which we are already trying to make some experiments is advanced monitoring. So mechanism to capture monitor information in networks and distribute it, putting information in packet headers. Also, deterministic networking is another use case that may benefit from this EIP, network slicing, and so on. So the idea, we will define an EIP header, and in turn, we want to carry this IP header into the IPv6 header. Where do we carry in the IPv6 header? Either we can carry it in a hop-by-hop option, or we can also carry it in segment routing header TLB. So I can also refer to previous presentation by Suresh. So also this mechanism is compatible with segment routing, and it can also be used to extend segment routing to add some missing bits, because as Suresh mentioned, also segment routing for IPv6 is meant to be extendable, and so we can put the extension in the SRH TLBs. So we have started here. You find the link to another document, which is we have not yet published as an IETF draft because we are making a lot of revisions. We are working on it, but we hope that in a short time we can also publish as a draft. But in the meantime, it is published available at the link provided here. So we know that IPv6 header is already extensible by definition. There are extension headers and options inside the extension header. So why we are putting this level that we call it extensible in-band processing? The main reason is that there are practical barriers and problems to the extension process of the IPv6. So there are standardization hurdles, and there are some difficulties doing implementation and experiments. So we believe that adding this extensible in-band processing solution will reduce the pressure on the standardization, and I will show something in the next slides. And also that we are building open source prototypes of these EIP ideas that can help in the experiment, and so in developing the solution. So in the draft that we have published, there is an analysis of the several ongoing proposals and discussions to allocate hop-by-hop options for different use cases. So I have mentioned, I've listed at least 7 different proposals that are currently requesting, and some of them are also close to becoming an RFC. They're requesting new hop-by-hop options because, of course, it's I mean, it's a hot topic. It's a timely topic that you want to extend IPv6 by putting new features. But I think that if we go for a different hop-by-hop option for every use case, I mean, the solution does not scale. So we are trying to make a more general approach to have a single hop-by-hop option that then can be extended further with different use cases. And so we believe that there are good reasons for having a single EIP header that can be, as I discussed, either an hop-by-hop option or a TLB inside the SRH header if you want to extend the segment routing for SRV6 for IPv6. But it is good to have this common EIP header, and inside this we can put the EIP information elements that can support different use cases. Okay, this is one reason is that the number of option types in hop-by-hop header is very limited. So there are 8 bits, but then 3 of them are used for defining. They have a specific semantic. So basically, in some cases, you have only 32 options to define. While with our EIP information element, we have a code point space of up to 24 bits. So we have millions, 16 millions of different information elements that we can define. And so there is no pressure, let's say, on the standardization. And also another interesting thing is that common information elements can be reused across use cases. So it makes sense to have one single header, then different information elements, and some of them are reused across different use cases. So, of course, we will need to define a different information element depending on the specific use case that we want to support. But some of them, like timestamping or authentication, they will be shared. So we can create a library of common protocol components or common information elements that can support multiple use cases. And we have started to do this in the document that I mentioned before. Quick discussion on applicability and scope. So in our vision, we do not need EIP to work end-to-end across the internet, but we can have this header working in limited domains. And also a quick mention about security, that we are using an H-match approach that we can authenticate the information that the nodes write in this header, like this is done in SRV6, already done in segment routing, the same approach that is done to authenticate the information that you put in these headers. So here I repeat the draft. This is not the IETF draft. This is still a public document, not published as a draft, in which you will find the definition of this EIP header and a definition of a set of information elements that are carried inside this EIP information element. And so coming to the specific topic of semantic routing, we focused on a specific scenario of semantic routing. So we consider the need of routing using a geographical position, which is called geotagging. And this is one of the use cases that are defined in the semantic routing drafts that Daniel and Adrian has published. So we took the ideas from that drafts. So geotagging, of course, means carrying geographical coordinates in the IP pack, in the IP headers. And so we have a geotagging information element, which is carried inside the generic EIP header. And we can carry the geographic location of the source or of the destination of the communication. So of course the source can use it to advertise its geographic position, and other nodes can use for example, the advertised location to use it in a routing. Things, for example, to the situation in which you have LEO satellites that are covering the world. So in that case, maybe you need to, if you know the geographical coordinates, you can use this information to route an IPv6 packets in your network of LEO satellites. No. So here we have the details on how we can encode the information in our information elements. So we have a solution where we encode coordinates in 32 bits, and we have precision in the order of millimeters, or you can use 16 bits for latitude and longitude, and you have precision in the order of hundreds of meters. So these are all interesting things that you can do when you have a platform for doing experiments. So you move from theory to practical experiments and working code. And in fact, we have a prototype for our EIP. It's a prototype that is built for Linux, and we have two main components. We have a packet generator and a dissector, so we can write our EIP header, and we can put this EIP header inside the hop by hop header or segment routing TLB. And then we have an EIP aware router that is based on eBPF and can take these information elements and can take processing decision, routing decision based on the information. So we are implementing this semantic routing, in particular the geotagging use case with these prototypes. And also we are implementing advanced monitoring. So we have a solution for end-to-end delay monitoring in band, so adding information in IP packets to monitor end-to-end delay, and another solution for path tracing, so taking recording the path that a packet is taking, putting this information in our EIP header. Okay, these are some details on our prototype, which is included in a Docker container. So you can download your Docker container and you can experiment with a simple topology like this, generating your packets and then processing in a couple of intermediate routers. We have set up an informal interest group on this topic. So here you can find the link, and you're welcome to join, and you will find all the information about the prototype also in this link. Here you find some reference. We have recently we will have a paper in the workshop that also Daniel mentioned, I think, in the chat. The second workshop on future internet routing and addressing that describe this solution. And that's it. So thank you for your attention, and I'm happy to take questions.
Wonderful. Thanks, Stefano. I see Greg in the queue.
Interesting. So in advanced monitoring, you mentioned a couple of functions. So as it's a route tracing, I would imagine this is a hop by hop function.
Yes.
Okay. So what's your feeling about amount of information that you need to collect on path?
Yeah. Of course, you need to be very efficient in order to collect the information. And there is actually there is already a proposal on path tracing for for segment routing. It is a recent draft that has been posted in the segment routing communities. And for our path tracing, we simply reused that path tracing proposal that have a very efficient way of encoding the information of the different nodes in order to keep the size of the header limited.
Yeah. What I wonder is, is if I understand your proposal correctly, is that you propose to collect all their telemetry information within the trigger packet, within the data packet. Is that correct?
Yes. When you are using EIP for this telemetry, we are doing something which is similar, but there are existing already existing proposal in IETF. So in this case, we are doing something similar to the existing proposal.
Yeah, I just want to point that this is individual draft, so it would not be a really IETF document yet. But secondary, what I wanted to ask you, why you think that it's important or critical to have this information in the data packet itself and not to collect it out of band relative to the data flow?
Yeah. I think that in the case of monitoring, I think that there are advantages in some case in collecting information and sharing the information directly on the data plane. So if you are building a new router which is optimized for doing this information, I have the feeling that it's more efficient to do some operation in the data plane rather than exporting information in the management plane and processing this in the management plane. So if you need, for example, quick reactions, that's good to do. And also, there are some situations in which you can, for example, calculate some sketches, some reduced information in your data plane, and inserting this information directly in the packet can be more efficient. But of course, this is, I think, an open research topic at the moment. Yeah.
Yes. And another question I have is the information or advanced monitoring that you mentioned, very similar to what is already addressed by in situ OEM.
Exactly. Exactly. So my point is also this, that there are a lot of ongoing proposals and discussions to allocate op by op options for different use cases. So I'm also putting the question if it is, I think it's the right time also to make something which is a little bit more general, because with in situ OEM, you can do just monitoring, okay? But there are different other use cases in which you can also read, you can also write, you can also take decision based on the information that is inside. So my proposal is that we need a more general solution, and this is EIP is about a more general way of doing many use cases. One of these is semantic routing. Another one is advanced monitoring, and the proposal is exactly to have a generic framework rather than continuing to add new op by op options. So when the space is very limited.
I think a little bit differently, because if, for example, someone wants to collect geographical coordinates in addition to node IDs, the only thing that is needed is a new IOM data type. So because IOM trace data options are not fixed, it's registry. And as I understand correctly, so now it's a RFC 9197 IOM data. So you can add the data and then signal it in IAM header in according encapsulation, and you don't create a new.
Okay.
and you don't have to create a new header for that. Another advantage of IAM is it supports out-of-band collection of telemetry information, and it could be either IAM direct export or, for example, hybrid two-step. And hybrid two-step advantage is that it's not only keeps the overhead of the data packet limited by not adding data in the packet, but it simplifies the correlation of data because data are collected on the same path as the trigger packet in one in a train of packets. So
guys, this is good and interesting, but it's got somewhat off the topic of semantic routing.
Okay. Yeah.
I would encourage the two of you to talk about OAM to each other because it seems really relevant. And I wonder if just for the last few minutes, the chairs could pop up the last slide. While that's coming up, if you haven't been reading the chat window, you should. Amongst the very good, interesting questions, there's a masterclass in addressing naming, routing, and forwarding. Just a last opportunity for people to jump in and shout. Is semantic routing something that we should be looking at? Are there applications that use it? Is there a business case? Can we already solve the problems, and therefore we should work on extending existing toolkits or just using those toolkits? Should we build a point solution for each problem, or aim for a single generic solution? And what are the concerns about risks and benefits? I don't know if anybody wants to leap in with that. Nobody's showing. There was a really nice comment from in the chat from I think it was from Roland. About being concerned about putting too much state knowledge and information in the network and making the architecture much more fragile. But I still don't see anyone in the queue, so it's really interesting. Chairs, have you got anything that you want to say about this? Do I take silence as a no? Go on, Chenji, you speak.
Yes, checking here. Well, I want to volunteer some information regarding the first presentation on the what is driving the second routing, the slide. It used some examples, especially emphasizing the 5G related, some like collaborative video streaming, the 5G healthcare, VR, AR, holographic, those type of things. But the thing is like for these things, it normally comprised of multi-modality communications like video, audio, haptic, all kind of information that require the synchronization among different streams. So one information that has been discussed just in the finished 3GPP discussion for the XRM, it has a restriction only talking about the control plane without talking about the user plane. So here, well, what I'm looking at for the segment routing is look like it's talking about the user plane, like per packet processing with some embedded information. So yeah, I'm seeing the disconnection between the example that presented in the first presentation with the scenario or the domain that being applied, like a 5G related use cases. So yeah.
Okay, thank you. Jeff, do you want to try again? Jeff is having mic problems. No, still nothing from Jeff. Okay, Lixia.
Sorry, I'm multitasking so that I didn't volunteer to talk. But just a simple question. I think the semantic routing sounds interesting. As I asked on the chat, however, the very first question is what the identifiers identify. My current understanding of semantic routing is to still utilize IP addresses, but putting some so-called semantic meaning into it. Whose semantic is that? That's a question. It's the semantic of the applications, the semantic of the contents. I think this really gets into a change of architecture. If your semantic departs from IP address semantics, it's not about the details, whether you do point solution, you do something else. It's not about you can make an implementation that works in small scale. This is really about what semantics we are talking here. And if that semantics is not topological semantics, then it really represents architecture change.
Yeah, I think you nail it there. And to take this forward does require identifying what's trying to be achieved and therefore what needs to be expressed in the packet as a semantic. And then whether that goes by overloading the address field or by being placed somewhere else to, if you like, enhance the address field.
I just want to point out that an identifier space means one thing. If you want to put multiple definitions into the same identifier space, that one is an architectural change, two, the success rate is a question. IP already showed the example.
Yeah, I agree completely. Lewis gets the last word before Jeff.
Just very quickly, only to comment that, yeah, actually the interest on this that could help the applications to, I mean, help the delivery of the information to have some contextual information that could help to optimize the delivery of information from applications. So I think the interest on that, and I would like just to remark that because one of the values that you put there is if are there applications imminent to use this? Probably those that could require context will be the ones requiring this kind of information.
Okay, thanks. And over back to you, Jeff.
Yeah, my comment here would be to also follow what's going on in MPLS to the zero developments because pendulum always swings, right? Let's do everything in control plane versus let's do everything in data plane. While doing everything in control plane, we know it doesn't always work. Doing everything in data plane has huge cost associated with it, from forklift upgrades to very low success rate, as Xia said rightly. So finding way in between probably would be right place to use. And I can tell you from actual implementation perspective, there's a lot of work going on that's not published in ATF where the semantics are flattened. Otherwise, there's no way to put reasonable, simple device, what we call today mostly white boxes, to actually provide this functionality. Right. So we need to find right balance between what data goes into control plane, which is not necessarily what's going into forwarding plane, right? That's all on my side.
Okay, that sounds very reasonable. Thank you, Jeff. I guess time's up. Thank you, everybody, for contributing and typing frantically in the chat. And Dan and I are going to work on the minutes for the chairs to post.
So now with chair hat on, we are going to work with Engine and our ADs on trying to assess what has been presented and what could potentially be the next steps. Adrian and supporters on your side, please work on coherent proposal of how you perceive the presentation, the interest, and potential next steps. Please talk to us.
Okay, thanks, will do.
Thank you for everybody for attending the meeting. So we'll see you in Philadelphia.
Thanks, everyone. Goodbye.
Bye.